Questions 8 through 10 on the 2006 grade 12 Euclid math contest. If the log of x to the base 2 minus 2 times log of y to the base 2 is equal to 2, determine y as a function of x and sketch a graph of this function on the axes provided in the answer booklet. Log of x to the base 2 minus 2 times the log of y to the base 2 is equal to 2. Now we are going to use a log rule, one of many log rules, but the one we are going to use is the one that states that the log of m to the base b minus the log of n to the base b is equal to the log of m over n all to the base b, like that. So applying that rule over here, first, before we can apply that rule, however, we have to get rid of that 2 in front, and we can do that by bringing it over there and making that y squared. That's one of the log rules. And now we can apply this rule right here. So this becomes the log of x over y squared all to the base 2 is equal to 2. And then the fundamental definition of a logarithm gives us the fact that 2 to the power of 2 is equal to x over y squared, and therefore this becomes 4y squared is equal to x. Isolating for y, this would become y squared is equal to x over 4, and therefore y is equal to plus or minus the square root of x over 4. All right? Or some people might write it as plus or minus the square root of root x over 2, which either one is perfectly fine. Now, plus or minus, we've got two possible solutions for y, right? But this is where you have to look at whether or not both of these are possible, yes or no. It's very common in log questions or sine and cosine trigonometry questions where you get solutions, but one solution perhaps is inadmissible. So, since we have this term and we have this term in our original equation, that tells you something. It tells you that y is greater than 0. Correct? Since the log of y to the base 2 exists in the original equation, y must be greater than 0. Why? Because you can't take the logarithm of a negative number. All right? So that's the first one. And in the exact same way, since we have also y, we also have x to the base 2. That also exists in our original equation, and therefore that tells me that x must be greater than 0. So keep in mind greater than 0 for both y and x. So therefore the only possible solution is x is equal to positive root x over 2. The negative one is not possible because y cannot be less than 0. Now we have the relationship. That's perfectly fine. But now we have to graph this. Sketch a graph. So I'm assuming they just want something relatively basic. Okay. First thing I'm going to do is make a little bit of a table of x and y values. It doesn't have to be that long. I think, 8, 10, whatever you feel is sufficient to make a small sketch. I think that's all they're looking for. So x and y, and remember, x has to be greater than 0, so it cannot be equal to 0. All right, this is not allowed. So when we sketch our graph, we have to put a little circle where the 0 is, and I'll show you that a little bit later. Okay, wherever you want to start, I'll just start with a half, and then I'll just use integer values 1, 2, 3, 4, 5, 6, 7, 8. I think that's enough. That's good enough. And then for each one, of course, you just keep plugging the value of x back into that equation, and you get values of y. So just approximate. For a half, it's going to be about 0.35. For 1, it's a half value for y. For 2, it's about 0.7. For 3, it's about 0.86. For 4, it's 1 exactly. For 5, it's 1.1 approximately. 1.2, 1.3, 1.4, like that. Okay, so now we are going to draw a sketch. So let's draw a little x and y axis. Here is my y axis, and here is my x axis. Now, we are going from where? Up until 8, right? So let's say here 8, 4, 2, 6. It's just a rough sketch, as long as you have a certain basic idea. And then for y values, we aren't really going that high. So here we go. Let's sketch this. First and foremost, as I had mentioned earlier, where there's 0, the origin, the graph has no value. So there you put a little circle. Now we can plot this. For half, we got half as our very first one. It's about 0.35, so approximately here. For x equals 1, we got 0.5, so that's about here. And then just keep on plotting these. For 2, 0.7. For 3, about 0.8. And then for 4, it's exactly 1, so it's about there. And then 5, 1.1, 1.2, 1.3, 1.4, something like that, right? So it's basically a curve that looks like this. And that's all they're really looking at, is just a basic sketch of what this function looks like. And that's it. That's the requirements for question 8A. In the diagram, AB and BC are chords of the circle with AB less than BC. If D is the point on the circle such that AD is perpendicular to BC, and E is the point on the circle such that DE is parallel to BC, carefully prove, explaining all steps, that angle EAC plus angle ABC is equal to 90 degrees. Carefully. I like how they put that word in. Explaining all steps. All right. So what I'm going to do first is label the diagram, show you how this is done, and then I will explain and write out every single step. Because just labeling the diagram is not sufficient enough. They want you to completely explain every single step that you make on why that step is possible, why that step is true, and so on. So here we go. So first, let's write a few things on the side that are part of the question. AB is less than BC. All right? And they want us to prove that angle EAC plus angle ABC is equal to 90 degrees. So what I want to do is first label as much as I can, and then I will explain in detail. So EAC, well, that angle basically, first we have to draw a line. In order to make EAC, we have to draw a line from A to C. So let's do that. There you go. And then we have to draw a line from E to A. Okay, once we do that, then we can label EAC. So angle EAC is this angle in here, and that angle, I will label it as X. Okay. Next one, ABC. ABC, the good news is they've already drawn in the lines, and I will call that Y. So X plus Y is equal to 90. This is what I have to show. So I have to prove this. That's my goal in this question. All right, let's take a look here. This angle is 90 degrees. That's already been given. Now, they tell you in the question that AD is perpendicular to BC. So AD is perpendicular to BC. That's been given in the question. So if that's true, then this angle must be 90 degrees. All right? Now the reason that's true is because these are opposite angles. This angle is opposite of that angle, and therefore they must be equal. All right? And I will write all this out later, but first I want to explain it in the diagram. Now, we let ABC equal Y, correct? And we also let EAC equal X. So we are going to use those letters throughout. Now, this triangle is very important because we know two angles so far. We know Y and we know this, which is 90 degrees. So therefore this angle must be 90 minus y. Okay? Now at this point we have to connect a couple more lines. We have to connect C to D. So like this. All right? When you do that, you will notice the following. That ABC is equal to ADC. Angle ABC is equal to angle ADC. Now, why? Why is that true? ABC is right here, it's y, and that's equal to ADC, this guy. That is y also. But what is the reason? How did I get that? Well, the reason is because both of them are angles created from the same 2 points on the circle. And those 2 points I'm referring to are A, which is right here, and C, right there. And if you notice, if you take lines coming out from A and C, the first place you get in this diagram is B, so that angle is Y. And the second place that they show you is D, like that. And there's a rule that if you have angles that are created from the same 2 points on a circle, those angles will be the same. So there you go. That is y, and that is y. Y equals y in terms of my labeling. Okay, so in a very similar way, I can now label all 3 angles in that triangle. We have 90 and we have y, so this angle in here is 90 minus y. All right, so far so good. Nothing super tricky. Now, take a look at angle AFC, this angle right here. What is that? Well, it must be 90 degrees. How are we so certain? Well, because the angles about a line always add up to 180. Well, we know one angle is 90, so the other angle must also be 90. All right? So draw a big right angle like that. All right? Doing this slow because I want you to fully understand this. And then FDE, which is right here, FDE, this angle right here, that also has to be 90. Why is that 90? Well, because they tell you that DE is parallel to FC. DE is parallel to FC. They tell you that in the question. So therefore, this full angle right here is 90 degrees. All right? So we now know quite a bit about this diagram. We have to put it all together. Now the next step in our development of this proof will involve the following. 2 points, A and D. From those 2 points, they have created 2 triangles. The first is they've extended A and D to meet at E, and that creates this angle. And then they've done the same kind of thing, well, I've actually done it, by extending A to C and D to C. So by the same principle, as I explained a little bit earlier, those 2 angles are the same. So this angle and this angle are the same, and I'll call that W. And if you forgot what that principle is, it basically says that if you have 2 points on a circle and you extend them to create angles, those 2 angles will be the same. And in our case, angle AED is equal to angle ACD because they are both inscribed angles created from the same 2 points on the circle, and those 2 points are A and D. All right? So we are almost done with our proof. Now take a look at angle ACB. ACB, this angle right here. That angle, which I'll just draw like that, it's W minus 90 minus Y. W minus 90 minus Y. Correct? And just make sure you put the 90 minus Y in brackets. So it's w minus 90 minus y, and that is w minus 90 plus y once you take it out of the brackets. All right? Now, finally, the sum of the angles of any triangle is 180. And the triangle that I'm going to be looking at is this right here. ABC. That's the triangle that I'm going to be looking at. And before I add up all the angles, let me see if all the angles are labeled. I think there's one guy missing in here. That one is missing. That we can figure out pretty quickly from ADE. Notice in ADE I have, this is 90 degrees, this is W, so this guy in here must be 90 minus W. Okay, so there you go. Now we are ready for all the angles of ABC, and they all equal 180. So what are they? There's Y plus this guy 90 minus Y plus 90 minus W plus X, and I think the only one is this guy right here, 90 minus Y in brackets, and if you simplify that, it becomes W minus 90 plus Y. Okay, and this is all equal to 180. So let's do the math here. Let's collect like terms. Y minus Y, that disappears. 90 minus 90, that disappears. Minus W plus W, that disappears. And the only thing we're left with, I believe, is 90 plus X plus Y is equal to 180. And bringing the 90 to the other side gives you X plus Y is equal to 90. And there we go. We just completed the proof. That is what we wanted to do. Now, I did it with just labeling, right? So each of these steps I have to now explain in words. I can't just, label it and say, okay, let's call it a day. And that's why they put in the original question, carefully prove, explaining all steps, right? Okay, no problem. Now, to save you the boredom of listening to me go through every single step again, I'm just going to write it all out. And once I write it all out, I'll then read it to you. Okay, here we go. Angle DFC right here is 90 degrees. That's given in the question. Now, since AD and BC are perpendicular, that's also given in the question. AD and BC, those are perpendicular. That means that angle AFB, which is right here, must also be 90 degrees by opposite angles. It's opposite to this angle. Okay, so that's the first and second of the proof points. Number 3, since we let ABC, we let it equal to Y, that means that this angle BAF is 90 minus Y, since that's 90. Now we get to a very important part. That's why I put a little asterisk there. Connect C to D, and when you do, you will notice that ABC and ADC, those angles, ABC is right here, ADC is right here. Those two angles will be equal. Why is that? The reason is because both of those angles are inscribed angles created from the same 2 points on the circle, and those 2 points are A and C. All right? So that takes care of 4. Number 5, FCD, the angle FCD, which is right here, that must be 90 minus Y. Since that's Y and that's 90, so that third angle is 90 minus Y. Okay? And we also know that AFC right here is 90, and FDE, this is also 90. Why? Because FC is parallel to DE. That was given in the question, that piece of information. And then now we get to number 6, which is very similar to number 4. Look at AED, that angle. It's the same as angle ACD. Why? Because they are both inscribed angles created from the same points on the circle. In this case, we're talking about points A and D. This point and this point. You can create two angles by extending them. The first one is AED, and the second one is ACD, and those will be equal, and I've labeled them W. W here, W there. Okay? So we'll just say label them W. We always try to be as complete as possible in proofs. Okay, now we get to the last couple steps. Keep the diagram in the photo because we need that. Okay. Now, last few steps. ADE, which is this one. Where's D? D's hiding. Oh, there's D. ADE. So ADE, that's a 90-degree angle. And therefore, angle DAE, DAE is going to be 90 minus W, because this is W. Okay? And then ACB, this right here, that we can get because we know this whole thing is W, and this angle is 90 minus Y. So to get ACB, you just subtract W and 90 minus Y, as I've done right here. And then finally, we can add all the angles of triangle ABC. And I think I've labeled everything in that triangle, and I've described why everything is labeled as such. Correct? And the sum of the angles of ABC, of course, are 180, and those are X, this guy right here, 90 minus W, 90 minus Y, Y, and finally W minus 90 minus Y, those angles. And they all equal 180. And when you simplify and collect like terms, it'll get down to there, X plus Y plus 90 is 180, and then bring the 90 over to the other side, and there you go. And in the very beginning of the question, I had denoted that angle EAC was X and angle ABC was Y, and there you go. I've proven that the sum of those two angles is 90. And like always, in any proof, try to be as complete as possible, try to explain everything as possible, as complete as possible, and they even tell you that, right? They emphasize that in the question. If you look back, they tell you, carefully prove, explaining all steps. And I think I've done that. So that completes 8B. Number 9, define f at x to be equal to sine of x all to the power of 6 plus cos x to the power of 6 plus k times sine x to the power of 4 plus cos of x to the power of 4 for some real k, real number k. Determine all real numbers k for which f at x is constant for all values of x. Our equation is f at x is equal to this big long expression, right? But the good news is that we know something that will help us, and that is the following. Sine of x squared plus the cos of x squared is equal to 1. And this is always true. That's a property. And we can use that. We can isolate for one of these. Instead of having coses and sines, we can just put everything in terms of sine by making that substitution. All right? And to make things a little bit easier in terms of the way it looks, instead of having to write sine x every single time, I'm just going to let sine of x equal to a. And at the very end, we can always substitute it back. Okay, so here we go. This will be much simpler. So this becomes a to the power of 6 plus cos, well, we are going to substitute, right, for this. So it's going to be 1 minus a squared, correct? And that's all to the power of 3. Right, because it's cos to the power of 6. I've broken it up into squared and powers of 3. And then this is going to be sine of x to the power of 4, so that's a to the power of 4, and then cos squared to the square, right? And that's just going to be 1 minus a squared, all squared, like this. Okay, simple substitutions. Makes things easier for us. All right, now we've got to do a little bit of algebra here, expand this all out. It shouldn't be too bad. It could be a lot worse. So let's see here, expanding that, I get 1 minus 3a squared plus 3a to the 4th minus a to the 6th, and then plus k, and then in these brackets we're going to get a to the 4th plus 1 minus 2a squared plus a to the 4th, like that. Now let's see if we can collect any like terms. I think not much cancels, but the a6 cancel, so that's good, right? And then for the k part, we can combine those a to the 4ths like this. And I think that's about as far as we can go there. All right. So far, so good. Now let's put this all out in terms of one big long equation, and then we'll try to collect like terms in terms of powers of a. So k2a squared, like that. All right, so let's collect powers of a to the 4th. What's going to be the coefficient? Let's see here. I bet it's 3 plus 2k, right? This guy and this guy. And then a squared, let's collect those coefficients. So minus 3 and minus 2k. And then we are just left with k plus 1. Okay? And I think these two can factor yet again, because those look very similar. So 3 plus 2k, if I put that out front, I'll get a to the power of 4 minus a squared. And then we just have this k plus 1. And this is equal to f at x. Now let's go back and read the question again. Determine all real numbers k for which f at x is constant for all values of x. Constant, meaning f at x would be the same regardless of what x is. That would be true if this whole expression vanishes. And therefore f at x would be equal to k plus 1 always, regardless of what x is equal to. How can this be equal to 0? Well, it can be equal to 0 if this is equal to 0. So, if 3 plus 2k is equal to 0, we will be able to get what we require. F at x will be equal to k plus 1. And what that means is that it would be constant for all values of x. Right? So, here we go. We got to figure out what k is. 3 plus 2k is equal to 0, so 2k is equal to negative 3, and therefore k is equal to negative 3 over 2. And that's the only value of k for which this holds true, that f at x is constant for all values of k. That takes care of part A. Part B, if k is equal to negative 0.7, determine all solutions to the equation f at x is equal to 0. So f at x, they want us to set it equal to 0 and then solve for x. Okay, well, we had originally figured out an equation, right? So we will use that. All this hard work should not go to waste. We'll just use that same equation. F at x is equal to 3 plus 2k times a to the 4th minus a squared plus k plus 1. And recall that I had let sine of x equal to a. Just in case you're wondering, what is a? That's the sine of x. Okay, so here we go. Good news is they tell me that f at x is going to be 0. And they also give me the value for k. So this becomes 3 plus 2 times minus 0.7. And the rest is just a to the fourth minus a squared, and this is going to be minus 0.7 plus 1. All right, so if you simplify this, you will get 1.6 a to the fourth minus a squared plus 0.3. So this is the equation we have to solve. Well, it shouldn't be so bad. It looks kind of like somewhat like a quadratic. Okay, now let's see here. What's the quickest way of doing this without too much algebra? If I multiply through, I think this will help me. I don't like these decimals. It's going to be harder to factor. But if I multiply through by 10, I think it'll be easier for me to factor. So that becomes 16. Yeah, 16a to the fourth minus 16a squared. And then this is going to be 10 times 0.3. So 3. I just multiplied through by 10. And I think this will be able to factor without too much problem. 4a squared, 4a squared, and then 3 and 1, negative, negative, I believe. Negative, negative. 16a squared minus 4 minus 12. Yeah, that'll do it. Okay. That helps me tremendously, because that means that 4a squared minus 3 is equal to 0. So that means a squared is equal to 3 over 4. And therefore a is equal to plus or minus root 3 over 2. Now, don't forget, sine of x is what is a. So this is really what we're trying to solve. Okay, so that's the first one we have to solve. The next one is, of course, this guy. Don't forget him. That gives me 4a squared minus 1 is equal to 0. And therefore, 4a squared, or rather, just do it quickly, a squared is equal to 1 over 4. And therefore, a is equal to plus or minus a half. Right? And therefore, sine of x is equal to plus or minus a half. So we have to find all the solutions of x for 4. Sine of x is equal to positive root 3 over 2. Sine of x is equal to negative root 3 over 2. Sine of x is equal to a half. And sine of x is equal to negative a half. So I think I can do it by keeping it all on the same screen. I don't see why we have to lose sight of everything that we've done. So we have 4 possible values for the sine of x, and each of these is going to give us some solutions for x. All right, so let's go through these individually. The first one is the sine of x is equal to positive root 3 over 2, like this. Right? That's the first one. Well, if that is the case, then you can use your calculator on the Canadian exams, and you'll get x is equal to 60 degrees. And if you know the cyclical nature of the sine graph, it will also be true for x equals 120. All right? But we have to give all possible. So any single value of x of the form 60 plus 360n, where n is basically any integer, is going to work because it keeps on going, right? If you look at the sine graph, it keeps on going forever. And in a very similar way, for any value that is 120 plus 360n, it's also going to give you the same thing. And you can verify this in your calculator, and some of you don't really even need to be proven of that. All right, so this is true for all n that is element of the set of integers. Okay, so in a very similar way, we're going to do the other 3 cases. The next one is sine of x is equal to negative root 3 over 2. And that gives me x is equal to 240, or x is equal to 300. But those are certainly not the only ones. Any value of x that's 240 plus 360n, or any value of x that is 300 plus 360n will give me sine of x is equal to negative root 3 over 2. For all n that is an element of the set of integers. Any value of n that's an integer. Now we turn our attention to the sine of x is equal to a half, and then finally the sine of x is equal to negative a half. Sine of x is equal to a half, x is therefore 30, or x is equal to 150. And of course, in the same fashion, any value that is a multiple or adding 360 is also going to be perfectly valid to give sine of x equals a half. For all n element of the integers. And then lastly, negative 1/2, x is 210, x is 330, but it's also valid for 210 plus 360n, or 330 plus 360n, where n is any integer, positive or negative. So there you have it. That is the full solution to number 9b. (9c). Determine all real numbers k for which there exists a real number c such that f at c is equal to 0. Let's remind ourselves of our f at x that we figured out earlier. It was 3 plus 2k times a to the power of 4 minus a squared plus 1 plus k, and remember that we had set sine of x equal to a. Correct? All right. Now, they are saying that f at c is equal to 0. So they're basically setting this equal to 0, and they are asking us to place c wherever there's an x and figure out what is the solutions for k. Okay, so let's work with this here. Where do we proceed? Let's see. So the first thing is we have to be consistent with everything that we use here. So, for example, if I have let sine of x equal to a, then if I square it like this, it becomes a squared, right? And a squared is in my equation. And if I take the fourth power like that, that becomes a to the power of 4, and that's also in my equation. But to make life easier, instead of using squareds and fourths, I'm just going to use b as a substitution for a squared. I think that will be a little bit easier. So let me put that in there to illustrate that a squared will be b. Okay, it's going to make things a lot easier for us, trust me. And therefore a to the fourth will be b squared. Okay, so a simple substitution like that will probably give us less headache in the long run. So this becomes b squared minus b. Okay, and the rest is exactly the same. It's not too big of a change. All right. Now let's multiply this out. So this becomes 3 plus 2k times b squared minus 3 plus 2k times b, and then this lone 1 plus k out in the end there. Now notice this looks like a quadratic, correct? And that's exactly what I wanted. It'll make things a lot easier for us. Now, the first thing is we have to solve this quadratic. And when we do, it will help us figure out what k is. K is most likely going to be a range of numbers. And step number 1 in this question is to understand that this quadratic will have real solutions only if the discriminant is greater than or equal to 0. So let's figure out what is the discriminant. Well, recall it's b squared minus 4ac, right? But just be careful. What is our b, what is our a, and what is our c? In our case, we have the following: minus 3 plus 2k. That is our b, all squared. Minus 4, our a is 3 plus 2k. Right? I'm looking at these guys. And my c is 1 plus k. And that has to be greater than or equal to 0. Okay? So I think we can move that up a little bit. All right, we've got a little bit of algebra here. So we got 3 plus 2k times, in brackets, we're going to have 3 plus 2k minus 4 times 1 plus k, and that is all greater than or equal to 0. And then simplifying, we get 3 plus 2k, and in the brackets, it's going to be minus 1 minus 2k greater than or equal to 0. And I think this will just become 3 plus 2k. The negative is going to flip the equality or inequality to make it like that, right? Because you have to factor out that negative. Now, this is going to be true when, if, let's see here, if 3 plus 2k is greater than 0 and 1 plus 2k is less than or equal to 0. All right. So from the first one, we will get that 2k is greater than or equal to minus 3, and therefore k is greater than or equal to minus 3 over 2. Okay? And then from the second one, you get 2k is less than or equal to minus 1, and therefore k is less than or equal to minus 1/2. And then if you combine these two, you get k is less than or equal to minus 1/2, and k is greater than or equal to minus 3 over 2. All right? So this is what range k has to be in for us to be able to get real solutions. But there's one little point that is very difficult to remember. Not extremely difficult, but a lot of people would probably forget this. That, remember, in an earlier part of this question, we had gotten that k is equal to minus 3 over 2 when f at x is a constant. Correct? So, since k being equal to minus 3 over 2 will give a constant, that means there's no roots for f at x. So the value of k equals the minus 3 over 2 has to be omitted. So we have to omit minus 3 over 2 from our inequality here. So basically all that means is that it just becomes k greater than. We just don't put this equals. It seems like a small thing, but it'll probably cost you a point if you miss that. All right, so this is what we are left with. Now this just tells me that we get real solutions. We still have to figure out the value for b in our quadratic and get solutions for that. So let's remind ourselves what was our quadratic. It was right here. And now we have to use the quadratic formula to solve for b. So, using our quadratic, b is equal to minus b, don't get confused with the b's. I mean, I know you're using b to describe two different things. Probably not the best choice of letters, but it's okay. I mean, you guys are smart. You understand. Minus b, so that's going to be 3 plus 2k, plus or minus the square root of b squared, which is 3 plus 2k, negative 1, all squared, minus 4ac, 3 plus 2k times 1 plus k, like that, all over 2a. All right, so here we go. Now we've got to simplify this. All right, 3 plus 2k plus or minus. In the brackets, let's see here. If I factor, I think things will be a little bit helpful for me. 3 plus 2k, and this will be 3 plus 2k minus 4 minus 4k, like that. And then on the bottom, not much changes, 3 plus 2k. And I think this will be 3 plus 2k plus or minus, simplifying this, 3 plus 2k, and then collecting like terms, minus 1 minus 2k. And I think that's about as far as we can go there. 3 plus 2k. All right? And if you break this up, you'll get a little bit of a simplification here. 3 plus 2k over 2 times 3 plus 2k, like that. And then this will be plus or minus, let's see here, minus 3 plus 2k. I'm going to break that up into two separate radicals. That's perfectly allowed. Minus 1 minus 2k, like that. And then this is going to be over 3 plus 2k. Okay? And when you do that, this becomes just a half, so that's great. And then this becomes, let's see here, minus 1 minus 2k, and all over the root of 3 plus 2k. Yeah, there you go. That's about as far as I can get. Now let's recall, what is b? Probably forgot what is b by now. And it was, b was a squared, which is the sine of x squared. Okay? We forgot. Well, I forgot. b is equal to the sine of x squared. Now, if you remember, the sine of x, in terms of a range, is between 1 and negative 1. So the sine of x squared, its range is between 1 and 0. Its biggest and smallest possible values. So that means since sine of x squared is b has a range between 0 and 1. Okay? So for this to be b, it has to be between 0 and 1, that part. And that will be true. b is less than or equal to 1, is greater than or equal to 0, if this guy in here is between a certain range. So that is negative 1 minus 2k square root all over 3 plus 2k square root. And that has to be between 1 and 0. Try it. If you put that in, you'll see that that will make this hold true. When it's 0, it just becomes a half for b. When it's 1, it makes that just a half. And if you do 1 half plus a half, you get 1. And if you do a half minus a half, this guy, you get 0. So this is a very important part of the question. Now we continue exactly with that. How? Square everything. If you square everything, you get rid of the radicals, and that will be very helpful. 3 plus 2k. And then the square of 1 is just 1, the square of 0 is just 0. Now we solve for this. And in particular, we have to solve for obviously the value of k. Now, before we continue, let's remember that we had gotten a value, or a range at least, for k way up there. If you remember, it was right here. So I'm going to write that again. I don't want to lose that because that's obviously very important. So it was minus a half that k is less than or equal to, and it was just greater than minus 3 over 2. Okay? So we have to keep that in mind, because whatever we get here, we have to combine it with this, because both of these have to hold. All right, so with this one, first let's concentrate on this guy. That would give me that minus 1 minus 2k is greater than 0. Or greater than or equal to, right? Because I just cross multiplied. And therefore that would give me that minus 1 is less than or equal to minus 2k. That should be positive 1. And therefore k is going to be, this will flip, less than or equal to minus a half. K less than or equal to minus a half, and that's consistent with what we got there. So that's fine. And then now we concentrate on this inequality, and that would give us minus 1 minus 2k is less than or equal to, if you cross multiply, 3 plus 2k. So collecting like terms, let's see here, bring the 3 over, and we get minus 4 less than or equal to 4k, and therefore k is greater than or equal to minus 1. All right, so we've got, if you combine these two together, this and this, that means k is less than or equal to minus a half, but greater than or equal to minus 1. And then of course we have to combine this guy with this guy, right? We have to get the common values of k that make both of those satisfied, and if you do, you get the following. And when you combine these, you get k is less than or equal to minus a half, and it's greater than or equal to negative 1. And that is the answer to part C of number 9. Points A1, A2, ... until AN are equally spaced around the circumference of a circle, and N is greater than or equal to 3. 3 of these points are selected at random, and a triangle is formed using these points as its vertices. Part A, if N is equal to 7, what is the probability that the triangle is acute? A triangle is acute if each of its 3 interior angles is less than 90 degrees. Now, if you have a circle, right, there's a fundamental rule that I'm sure many of you know, and that is if you have a diameter like that, and you draw a triangle within that diameter like this, any triangle where one side is the diameter and the other two sides touch the edge of the circle as I have drawn, there's a rule, and that rule is that this angle will be 90 degrees. Okay, so that's the first thing that we need to discuss. Now, if you draw another triangle in a similar way, but instead of the diameter, you say use a length that is not the diameter, I've moved it up a little bit, and then you draw any kind of triangle, what happens? Well, it's a little bit difficult to see in this diagram, but I'll tell you, this angle is now greater than 90. It's not acute anymore. Okay? So that's very important to understand. In words, that means that if a triangle is inside a semicircle, that angle will be greater than 90 degrees. If a triangle is within a semicircle, the angle will be greater than 90 degrees. Okay? Try to make this as simple as possible, and don't want to make this too confusing too quickly. So we want to create a situation where we create triangles that are acute. So there has to be some sort of a rule, some sort of a system, instead of sitting there all day long and trying to figure out, is this acute? No, that doesn't look acute. Oh, this is acute. That's going to be just terrible. So the rules are pretty straightforward to doing that. The first rule is that, I kind of hinted at it, is that we can't draw a triangle such that it's all on one side of the semicircle. Okay? Now, that is something that I've just shown you. The triangle must have the following two things satisfied. Rule number 1, each of the 3 arcs into which the circle is divided by the vertices of the triangle is less than half of the circumference of the circle. So let me draw a circle and a triangle and illustrate what this rule means. So here we have a circle, and that red line is the diameter that I drew across, and then I drew a triangle in green. Now, each of the 3 arcs, what are the 3 arcs? This is arc number 1, this is arc number 2, and this is arc number 3. Okay? Each of those 3 arcs into which the circle is divided by the vertices of the triangle, these are the vertices, first vertice, second vertice, third vertice. Each of those arcs is less than half of the circumference of the circle. Is that true? Well, first of all, what is half the circumference? Half the circumference, for example, would be like that, from one point on the diameter to the other. Are each of these arcs less than that? Well, this one definitely is. And just from inspection, I can clearly see that is also less than half the circumference, and so is that. So that basically means that this green triangle satisfies rule number 1. Now, there's one other rule that I want to mention. I think that should be sufficient. The triangle contains the center of the circle. Now, does this triangle contain the center of the circle? What is the center? Well, it's approximately here, right? That's the diameter. So the center is about there. Is the center inside the triangle? Yes, it is. So for this particular triangle, I have satisfied both rules. And therefore, that means this triangle is acute. Triangle is acute. So, this is the rule we have to follow. The first thing we have to do is make sure that we don't draw a triangle so that it's entirely in one half of the circle. And then, that's pretty straightforward. Then I have to follow 2 rules. This rule is pretty straightforward also. It's not that hard to make a triangle where the center is inside. But this rule, this one right here, is something we have to pay close attention to. Okay? So here we go with 10a. I'm going to keep the rules, but I'm going to delete these circles and start fresh with a circle with 7 points. All right, here we go. So here's my circle. I've put 7 points, A1 through 7, and I've drawn a diameter in red. Okay. Now, let's proceed with casework here. Let's say I've got A1 as my first point. Now I've got to figure out where can I put my second point. I don't really know, so I'll just say A2. Why not? If I choose A2, now I have to choose my third point to create the triangle. I don't know. Could it be A3? Well, let's see. And initially, we'll go through these, and then, of course, once you get the hang of it, we certainly don't have to go through every single one. If this is my triangle, A1, A2, A3, I look at my rules. Let's look at this rule first. It's the easier rule. Does the triangle contain the center? Well, where is the center? Center is approximately here, right? Well, no. This triangle does not contain the center, so immediately it's disqualified from being a possible choice. Got it? All right, so A3 is out. How about A4? Okay, let's do that. Again, draw in, what do we got? A1, A2, and A4 this time, right? Okay. Again, does it contain the center? Center is approximately here, right? No, so that one's out. So I hope you can see how we are trying to eliminate possible choices. How about A5? Let's see here. If A5 is possible or not. Okay? A1, A2, A5. And I think so. Yeah. The center is going to be approximately there. So A1, A2, A5 is going to work. Okay, great. I haven't even talked about rule number 1 yet, but rule number 2 seems to be the easier one, so let's just keep that. Now let's move to the next one. A1, A2, how about A6? Is that going to work? Well, let's see. A1, A2, A6. Nope. The center is not going to be inside, so that doesn't work. And then A1, A2, A7, well, that is wrong because remember, we can't have a triangle all within one part of the semicircle. So I hope you understood by using these rules why so far only A1, A2, A5 works. So we've exhausted the A2s, now we get to A3. And in the same way, I'll go through these. Once I go through them all for A1, we're certainly not going to go through A2, A3. There is going to be a pattern. Okay, A1, A3. What's my third choice here? Can it be A4? Let's see. A1, A3, A4. No, it does not. And just in case you're wondering, well, you haven't even talked about rule number 1 yet. Can you discuss that at least? Okay, well, let's discuss that. This triangle doesn't qualify because it doesn't meet both rules, right? The first rule, of course, is, well, that I keep talking about is the one there. The center has to be contained. The center is here, right? It's obviously not inside. But look at this first rule. Each of the arcs has to be less than half the circumference. Well, one of the arcs that is created is obviously bigger than the half circumference, correct? Just by inspection you can see that. So that triangle doesn't satisfy either rule. So A4 is out. What about, what's next? A5. Okay. A1, A3, A5. Let's see here. A1, A3, A5. Yeah, this one works. This one is definitely a keeper. So it works because it satisfies both of my rules. Great. All right, now moving right along. A1, A3, how about A6? Let's see if that one works. And the answer is yes, it does. It satisfies both of those rules. The center is inside, and the arcs, none of those arcs are greater than half of the circumference. This is probably the greatest arc, and it is less than half of the circumference. So there you go. That one works. Okay, I hope you're getting the hang of this. I'm doing this slow for a reason because it's a hard question and I want you to understand it. I don't want to just, go through it in a quick way and then it's useless. All right, so far we got 3. And have we exhausted the A3s? No, not yet. We have to do A7. Well, A7, I think you will be able to figure out. It's not going to work. A1, A3, A7 is this guy. And that doesn't include the center. And one of the arcs is way bigger than it should be. Okay, so that one's out. All right, we exhausted the A3s. Now let's move to A4. A4... So A4 and then what? A1, A4, and what's our next choice here? Well, we can't go back. We can't use the A3s and A2s because we've already talked about A2s and A3s. We can only move forward, right? So this one, let's see. Can it be an A5? Well, let's draw it in, A1, A4, A5. And yes, that definitely works. It will satisfy both of those rules. I don't have to keep talking about both of those rules and trying to justify and explain both rules to you. By now you get it, right? So that one works. Okay, next one, A1, A4, A6. Let me just draw it in quickly. A1, A4, A6. Yes, that does also satisfy both of those rules. And finally, the last one, let's see. A1, A4, A7. Is that going to work? Let's see here. A1, A4, A7. And yes, that also works. Okay, great. We are almost done. A1, now we're moving on to A5s, right? Okay. A5 will be pretty quick because there's only two possible choices, A1, A5, A6. And then A1, A5, A7. Because remember, we can't go backward. We've already exhausted the A2s, 3s, and 4s. We don't need to talk about them. A1, A5, A6. A1, A5, A6. Nope, that's no good. So that one's out. And then finally, A7. And I'm pretty sure this doesn't work. A1, A5, A7. Yeah, that doesn't work either. So remember, don't forget our rules. The rules are there for a reason. And then now we've exhausted the A5s. We move to the last one, which is A6. And A6, we don't have to talk about A2, 3, 4, or 5. We've already talked about those. The only one to talk about is A7. And let's see here, A1, A6, A7. And that obviously is not going to satisfy our rules. So there you go. For A1, I got 6 triangles that satisfy my rules and are therefore acute. Okay? So I did that slow for a reason. I did every single case for a reason because I wanted you to understand how this works. Okay? So how many did I get? I got 6, right? And in a very similar way, you will get 6 for each of A1, A2, A3, all the way up to A7. So just like how I did for A1 as my first vertice, if you do the exact same process for A2, then for A3, and so on, you'll get 6. So the total is 6 times 7, right? Because there's 7 vertices, and for each you get 6, which is 42. All right. Now, this is a probability question, correct? Let me just move this over here. We don't need to talk about the rules anymore. It's a probability question, and like any probability question, the numerator is what we want in terms of our specific condition, and we got 42. The denominator is the total, always the total. So what's the total? The denominator. From 7 vertices, we have to choose any 3. 7, choose 3. And if you're in grade 12, you definitely are familiar with the choose notation. So this is my probability. 7, choose 3, which is 7 factorial over 4 factorial over 3 factorial, right? So 42 over, that is going to be 35. All right, you can just do that in your calculator. All right, well, I got 42 over 35. Well, probability of something can never be greater than 1. 42 over 35 is greater than 1. So what happened? Why is this incorrect? Obviously incorrect, right? Well, here's the reason. There's nothing wrong with the denominator. That's fine. 7, choose 3. This number overcounts. The good thing about this question is that there's no way you can write that and move on. You will know as soon as you make the probability fraction that something is wrong. And in a way that's good because you will be able to go back and try to figure out what is it that I did wrong. The 42 that we calculated is indeed fine the way we did it, but we overcount. Why do we overcount? Because each triangle, when we do the system, will be counted 3 times. For example, in these, right, that we did so carefully, one of those triangles is A1, A2, A5, correct? Okay, A1, A2, A5 we got. But if you were to make A2 as the first vertex and go through the exact same system, one of the triangles you're going to get is A2, A1, A5. And that's the exact same triangle. And very similarly, if you use A5 as your first vertex and go through that system, you're going to get A5, A1, A2. And that's also the same. So these three are the same. So that basically means these 42 triangles that you got, it's basically 42 divided by 3 unique triangles. Does that make sense? So 42 divided by 3, which is 14 unique triangles. That 42 basically overcounts. It counts each triangle 3 times. All right, so that's why this was not working. You don't put 42 in the numerator, you put 14. All right, so 14 over 35 is our answer. Of course, we're going to reduce that to lowest terms, divide top and bottom by 7, and you'll get 2 over 5. And that is the answer to number 10A. (10B). If n is equal to 2k for some positive integer k is greater than or equal to 2, determine the probability that the triangle is acute. So it's the same story, but instead of 7, now they're telling you that n is equal to 2k. All right? And that k is greater than or equal to 2. So it's the same kind of question, but instead of 7, it's 2k. All right, so let's label this 1, and then we have no idea what n is equal to, but I'm just going to label it. Now, keep in mind, just like a clock, the point that is going to be completely diametrically opposite is k plus 1, and then it kind of goes on from there, k plus 2, and the very last one will be 2k. Correct? And this is, of course, k, which is diametrically opposite 2k. If you were to draw a line directly across, like that. Same thing with 1 if you draw a line directly across. Okay? So that is sort of the initial setup of this question. And I'll just connect 1 to k just to kind of illustrate that those are diametrically opposite. And 2k to 1, like that. All right? So, in the exact same way, we are going to figure out what is the possible choices. Now, remember our rules that the arcs have to be less than half of the circumference, correct? That was our first rule, circumference over 2, and that has to contain the triangle center of the circle. So this is rule number 1, rule number 2. Correct? All right. Where do we want to start? Well, first and foremost, because it's a probability question, as always, it's going to be a fraction, right? Now, this part is what we will figure out through trial and error. Well, not trial and error. There's going to be a system. The denominator is what I can figure out pretty quickly right here. And that is, remember, before it was 7 choose 3, where we had 7 as n, and we chose 3. So really quickly, pause it. What is it going to be here? Not 7 choose 3. This time n is equal to 2k. So it's 2k choose 3. This is the total number of choices. All right? Now the numerator, the box here, that's what I have to figure out. And then we will simplify it at the very end. Okay, here we go. Very simple in terms of the process, but it's a little bit more complicated considering the fact that it's 2k. Start as we did before. A1 is my first vertex. What can I put for my second vertex? Well, I don't know. Let's try A2. Well, before I try A2, what are the possible choices? Well, it can be any vertice between BW between A2 to AK. Right? Why? Why can't it be beyond AK? Why can't it be AK plus 1? Because if it was AK plus 1, then it would basically be entirely on the diameter. And then if you chose any third vertice here, that's not going to be an acute. It's going to be a right triangle. Remember, I discussed that if the diameter is part of the triangle. Now, okay, you say, okay, I'm convinced about k plus 1, but why can't it be k plus 2? Well, because if you have 1 and then k plus 2, and then you chose any point in between, then that also doesn't work. Because remember, the triangle cannot be entirely in one half of the circle. Remember, I talked about that previously. So the only possible values for the second vertice are between A2 and AK. All these guys. All right? So that's the first thing I wanted to mention before I start putting in values. All right, so let's choose A2. Now we get to the third vertice. What can the third vertice be? Well, first and foremost, let's talk about what it could be between. What are our choices? It has to be between AK plus 2 and A2K. So that means it has to be between this guy and this guy, correct? For the same reasons. It can't be any of these guys. If we choose this and this, it can't be k plus 1, the third vertice, because if it is, it will be entirely on a diameter, and that's not an acute triangle, it's a right triangle. If we choose k, then that entire triangle will be inside one half of the circle, or inside the semicircle, and that also does not work. It will not be an acute. And similarly, if it's 3, obviously, it doesn't work. So the only choices for our third vertice are between k plus 2 and 2k. Okay? So let's try k plus 2. If we have k plus 2, that again doesn't work. Why doesn't it work? Because 2 and k plus 2 are diametrically opposite from each other. So that basically means that this guy is a diameter. So that doesn't work. What about if we tried like k plus 3? If we do that, you'll notice that it doesn't contain the center of the circle, which is one of the requirements. So for this guy, what's interesting is that there's no possible value for the third vertice, for A1, A2. So I'm going to write here possible triangles. For this first scenario, 0. All right? So I hope that made sense. I hope. All right, let's go for the next one. We're going to keep A1. Okay? Let's try A3 this time. We exhausted the A2s. If we have A1, A3, the only possible choice for the third vertice is AK plus 2. All right, let's talk about this. We have A1 and A3, right? Let's say we want AK. Can we make a triangle? No, because it's going to be all in one side of the semicircle. How about AK plus 1? No, because then that becomes a diameter and this becomes a right angle, and that's not an acute triangle. AK plus 2 is the only one that works, and there you go. But what about other values? How about AK plus 3? Why would that not be a choice? Oh, watch what happens. If you do that, notice AK plus 3 and A3 are diametrically opposite, so this is a diameter, and therefore this is a right angle. It's not acute. And if you keep going like this, let's say I chose AK plus 4, like that, then we'd run into the problem where we cannot satisfy both of those rules. The center is here, it's not included inside the triangle, and the length of one of these arcs is greater than half of the circumference. Okay? So that means that for A1, A3, the only choice for that third vertice is AK plus 2. All right, so we exhausted A3s. Let's move on to A4. For A4, in a very similar way, if you keep doing this, you'll see that there's only two possible ways of making this triangle, A1, A4, AK plus 2, and A1, A4, AK plus 3. Okay? So the same kind of system. And by this point, you know, you're an expert, so I don't need to go through every single possible. You get it. I'm sure you get it. Okay, so how many possible triangles? Let me fill out this little table here. I got 0 for this guy. For the A1, A3 scenario, there's 1. For the A1, A4s, there was 2. And then very similarly, you will notice that if you keep doing this, you will get a following type of pattern. For A1, A5, A1, A6, A1, A7, all the way up to A1, AK, you will get the following. For this guy, you'll get 3 possible. For this guy, you'll get 4, 5, and you will get K minus 2. So that is basically the pattern in terms of the possible number of triangles. So to add up all of these, it's really just the sum of 1 plus 2 plus 3 all the way up until K minus 2. And you all remember that formula, right? If you're adding consecutive numbers from 1 till n, it's n times n plus 1 over 2. So if you use that, this is going to be K minus 2 times K minus 2 plus 1 all over 2. And that is K minus 2, K minus 1 or all over 2. Okay? Now, please note this was only for A1. Correct? We have to do this exact same scenario for how many? Well, how many were there? Everything from A1 all the way to A2K. So we have to do the same scenario for A1, A2, all the way till A2K. There's 2K vertices. So that means we take this number and multiply it by 2K. So to get the total number of triangles, you would multiply 2K, since that's how many vertices we have, times what we got for just A1, which is this right here, which is K minus 2 times K minus 1 all over 2. And remember, this overcounts because remember in the previous part we had a number that we had to divide by 3 because each triangle was counted 3 times. So we have to do the same here. We have to divide this by 3. And let's simplify this a little bit. This basically becomes K times K minus 1 times K minus 2 all over 3. So my probability is going to be K times K minus 1 all over K minus 2 all over 3. And the denominator, if you remember, it was 2K choose 3. Right? I had written that up there earlier, right here. So here we go. Let's simplify this. Now the first thing I'm going to do is, instead of simplifying the top and bottom, let me just simplify 2K choose 3 over here. That's 2K factorial over 2K minus 3 factorial times 3 factorial. correct? And that is basically 2k times 2k minus 1 times 2k minus 2 times 2k minus 3 factorial, like that, all over 2k minus 3 factorial, and then this 3 factorial is just 6. Now when you do it this way, this allows me to cancel those 2k minus 3 factorials, and then let's see how much I can cancel. I think the 2 from the 2k and the 6 will cancel, and that will just give me a 3 here, like that, and then the rest will probably be the same, 2k minus 1 and then 2k minus 2. Okay, so that's what I'm going to place into my denominator over here. So the numerator stays the same for now, and then that's over 3, and then the denominator I just calculated to be k times 2k minus 1 times 2k minus 2 all over 3. So let's invert and multiply and see what we get. So we get k times k minus 1 times k minus 2 all over 3, and then this invert and multiply gives me 3 over k times 2k minus 1, and I'm going to factor out a 2 here, and that's going to be k minus 1, like that. 3's go, the k minus 1's go, and all that's left is just, oh, the k's go also. So great, the only thing that's left is k minus 2, and then on the bottom it's going to be, well, I guess we can just multiply it out again, 4k minus 2. And there you go. That is the probability of getting triangles when you have 2k vertices. So k minus 2 over 4k minus 2. Let's go back and read the original question. If n is equal to 2k, for some positive integer k greater than or equal to 2, determine the probability that the triangle is acute. The probability is going to be k minus 2 divided by 4k minus 2 for some k greater than or equal to 2. If n is equal to 2k for some positive integer k is greater than or equal to 2, determine all possible values of k for which the probability that the triangle is acute can be written in the form a over 2007 for some positive integer a. Well, recall in the previous part we got the probability to be equal to k minus 2 over 4k minus 2. And they are saying that you can express that in the form a over 2007. And they want you to figure out what are the values of k. All right, so let's cross multiply this and see if this helps us. If we do, we get 2007 times k minus 2 is equal to a times 4k minus 2, like that. Factor out a 2 and you get 2 times a times 2k minus 1, like that, and that left side will be pretty much the same. Now notice this is 2, so that means that this side is 2 times something, so therefore that side is even. If that side is even, that means this side is even. And since the right side is even, the left side is even, that means k minus 2 must be even, because that's the only way that an odd number like 2007 multiplied by something can become even. If k minus 2 is even, that means k must be even, correct? If k minus 2 is 8, then k is 10, which is also even. So since we've established that k is even, we'll let it equal 2m for some integer m, right? Because all even numbers are of the form 2m or 2k or 2 something. So substitute this into our equation and we get 2007 times 2m minus 2 is equal to 2 times a 4m minus 1, like that. And this, you can factor out a 2, and when you do, you just get m minus 1, and then that 2, when you factor it out, it'll cancel with that 2. So you're just left with this at the end. This is our equation. All right? Now, 2007, we're going to write it in terms of its factors, its prime factors, and I believe that's 223 times 3 times 3. I think those are the only prime factors it has. And now that we've got it in this form, we can make a table and see what we will get for m, and then we will figure out what is k. So here we go. And before I get started, I'm going to write that in a little bit different format. A over 2007, right? This is 2007 right here, is equal to m minus 1 over 4m minus 1, right? I just rearranged it. I didn't change it in any way. All right, so let's make our table. 4m minus 1 here, m minus 1, a, and k. All right, let's see. Well, 4m minus 1 is the denominator, and it's got to sort of be the matching denominator to the other side, right? So what possible values? Well, the only possible values are the factors of 2007, and those are going to be, 2007 itself. Let's see here, 3 times 223, which is 669, and then 223, 9, which is 3 times 3, and then 1. Correct? I think that's it. All right, very quickly we can figure out m. If 4m minus 1 is equal to 2007, let's see here. 4m minus 1 is equal to 2007. So that means 4m is equal to 2008. And therefore m is equal to 502. So 502 goes here. Therefore m minus 1 is 501. Correct? And this basically becomes a situation where we have m minus 1 over 4m minus 1 is equal to a over 2007. Correct? So, solving for a, m minus 1 is 501. 4m minus 1 we said is 2007. So that means a over 2007. Okay, well, a just matches this time. It's 501. Well, we have to figure out k. K is equal to 2m. So that means k is 1004. All right, great. We got one value for k. Let's keep going here. We got a little bit more work to do. Our next one is this one, 669. So 4m minus 1 is equal to 669. So that means 4m is equal to 670. And therefore, m is going to be 167.5. Okay, well, that's not going to work because m has to be an integer, 167.5. So we don't need to worry about these guys now because this is something that is not going to give us a proper integer solution, right? Because m has to be an integer. All right, keep going. Next one, 4m minus 1, we let it equal 223. So that means 4m is equal to 224, correct? And therefore m is equal to 56. So this is 56, m minus 1, therefore would be 55. Okay, so now we get to figure out what is a. m minus 1 is 56, or sorry, 55. 4m minus 1 is 223, and that is a over 2007. Cross multiply, and you get 55 times 2007 is equal to 223 times a. And solving for a, you will get a is equal to 495. So this is 495. Great. So k is equal to 2m, right? So 2m, m is 56, so 2 times that is 112. All right, we got two values for k. Moving right along. 4m minus m minus 1 is equal to 9. 4m is equal to 10, and therefore m is equal to 10 over 4. Well, that's not an integer, so this is not going to give us anything. All right, no problem. 4m minus 1 is equal to 3. 4m is equal to 4. m is equal to 1. So that means m minus 1 is 0. And that's no good, because if m minus 1 is 0, then this equation basically becomes 0 over 3 is equal to a over 2007. And that means a is going to be equal to 0, but a cannot be 0. A has to be a positive integer. Yeah, so this is not going to give us any solutions. Yeah, we got one more. 4m minus 1 is equal to 1. That means 4m is equal to 2. So m is equal to 2 over 4. And 2 over 4 is not an integer, so this doesn't give us any solutions. Okay, there's one more. Believe it or not, there's one more. And this one is figured out by getting the greatest common divisor. And it's tough. This last one, I mean, whoever gets this one, my hat's off to you. Really, how did you come up with this last one? I mean, give me a break. It's as follows. The last one, I'll just put it over here. By using greatest common divisor, GCD, you come to the conclusion that if you have a number like a over 2007, it doesn't have to be exactly in these forms. It can be in a slightly different form. And the form that they come up with using GCD is 6 over 27. And 6 over 27, if that is equal to m minus 1 over 4m minus 1, then that means that 4m minus 1 is equal to 27. So 4m is equal to 28, and therefore m is equal to 7 here. So they're getting 27, 7, 6 for m minus 1, and then a, it's a over 2007 is equal to 6 over 27. So that means 27a is equal to 6 times 2007. A is equal to 446. So 446 goes in here. And then k, well, k is equal to 2m, right? We know that. We've been doing that all along right here. So since m was 7, k is 14. So I guess that's what separates the 100 from the 99 on this math contest. How do you figure that out? I mean, come on. There's no way I would have been able to get that. I'm going to be honest with you. So this one, okay, I can live with that. But this one, you know, you deserve that 100% if you got that. So these are the possible values of k. And that completes number 10.